Doing mathematics means, above all, proving what one claims. We've seen that stereographic projection sends circles on the sphere not going through the pole to circles in the plane. And now, we're going to prove it. Even though this has been known for many centuries, it is I, Bernhard Riemann, who will present this proof to you. I'm frequently honored because one speaks today of the Riemann sphere. Proving is much more than showing. It's not enough to see in a movie that some curve looks like a circle to be sure that it is indeed a circle. A mathematical proof must use reasoning to be convincing and must explain why it is indeed a circle. The great Euclid, during the 3rd century before Christ, formulated the rules of the mathematical game in his book, The Elements. A proof has to rely on facts that themselves have to be proved. But one has to start with something, so that some statements have to be accepted without proof. These are the axioms. Therefore, mathematics appears as a gigantic construction whose foundation consists of the axioms, and such that each brick rests on the previous ones. In order to prove the theorem about the stereographic projection of circles, we should in principle start with the axioms. Of course, we have no time for that now. We'll assume we already know the theorems of geometry that are often studied in high school, and we'll prove this theorem. Start with something simple: the intersection of a sphere and a plane. We see that if a plane cuts a sphere, and if it is not tangent to the sphere, then the intersection is a circle. We can see it, but why is it true? How do we prove it? Let's consider an arbitrary plane colored in blue. We can draw the perpendicular from the center C of the sphere to the plane. Let's call P the foot of this perpendicular. Consider 2 points, A and B, on the intersection of the sphere and the plane. And let's look at the 2 triangles, CPA and CPB. They share a common side, CP. Both have a right angle, since the angle at P is of course a right angle, since the plane is perpendicular to CP. But note that the hypotenuses AC and BC have the same length because A and B are on the sphere and thus sit at the same distance from the center C. But recall the Pythagorean theorem. Since our 2 right triangles have 2 sides of the same length, their 3 sides have the same length. Hence we've proved that PA and PB have the same length. That is, that A and B are on the same circle with center P in the blue plane. Therefore, we proved that all points which are both on the sphere and the plane belong to some circle. Does that imply that all points on this circle are on the sphere and on the plane? A priori, no. We still have to prove it. Let A be a point which is on the sphere and the plane. Consider the circle in the blue plane with center P and that goes through A. We'll prove that this circle is contained in the sphere. Let B be some point on that circle. Look at the two triangles CPA and CPB. They share a side, CP. Both are right-angle triangles since the angle at P is a right angle. But the lengths of PA and PB are equal since A and B lie on the same circle with center P. Again, using the Pythagorean theorem, we conclude that the hypotenuses have the same length. CA equals CB. This means that the point B also lies on the sphere, since it sits at the same distance from C as A. That's it. We've proved that when a plane cuts a sphere, the cross-section is a circle. Let's look now at a diameter APB of our circle, and let's place it in the plane of the screen. The blue plane appears as a straight line on the screen, and the sphere appears as a circle. Let's draw the tangents to the circle at A and B. They intersect in a point S. Of course, the line CS is again a symmetry axis for our figure. Why? Well, because the triangles CAS and CBS are equal. Why? Well, because they are both right-angled triangles having a common hypotenuse, and the sides CA and CB have the same length. Why? Well, because these are two radii, of course. You see, if we had to go to the end of all the arguments, this film would be the longest in movie history. Look, we proved that any circle drawn on a sphere can always be thought of as the contact locus between a cone of revolution and a tangent sphere. If you like, the sphere is like ice cream in a cone. Well, we shouldn't forget what our aim is, to show that stereographic projection carries circles onto circles. Let's first prove what mathematicians call a lemma. Here is the tangent plane to the sphere at some point A, seen from the side. Now, here is the tangent plane at some other point, B, and also seen from the side. These two planes intersect along a line D, but presently we see only one point since this line is perpendicular to the screen. The figure that you're looking at is symmetric with respect to the bisecting line of the two lines that we see. This three-dimensional picture is symmetric with respect to the bisecting plane of the two tangent planes. Choose some plane containing the segment AB. It intersects the line D in a point M, unless it is parallel to D, of course. The figure's symmetry with respect to the bisecting plane shows that AM and BM have the same length. The triangle ABM is isosceles. Voila! That was our lemma. Now we can prove our theorem using what we just learned. Consider a circle on the sphere which does not go through the North Pole. We want to show that its projection is a circle. Look, if instead of projecting onto the tangent plane to the South Pole, we projected onto some other parallel plane, the famous theorem of Thales would imply that all the projections are similar. Hence, in order to prove our theorem, we may choose the projection plane as we wish. as long as it is parallel to the tangent plane to the South Pole, of course. So let's place our yellow circle in a cone. Remember, the ball of ice cream in a cone with vertex S. Well, we are going to project onto the horizontal plane through S. The point B projects onto a point D. But look at the figure. The triangles AMB and DSB are similar. Why? Well, again, Thales' theorem. Do you agree? Now, remember our lemma. The triangle ABM is isosceles. Hence, the same is true for the triangle BDS, so that BS has the same length as DS. When B moves along the yellow circle, the segment BS stays tangent to the sphere. Its length, therefore, remains constant. Since BS and DS have the same length, the moving segment DS also maintains a constant length. Let's see. Saying that DS has a constant length means precisely that D describes a circle with center S, so that the projection of our yellow circle on the horizontal plane through S is contained in a circle. We have seen that by Thales' theorem, this implies that the projection on the tangent plane to the South Pole is also contained in a circle. And this is what we wanted to prove.